Well, good morning. This is Wednesday morning, the 22nd of February, 2017, 9:35 in the morning. A little late getting started. I apologize for that, but I had been given some things to announce at Financial Services yesterday afternoon, and then when I announced it in my first class this morning, I noticed I didn't think we qualified, so I went down to ask, but the person I needed to ask wasn't there. So anyway, that's why I was a little late getting back here. But let me make a few announcements. These mostly pertain to my office hours. It's kind of a crazy time happening right now, at this point in the term. First and foremost, right after class today, we have this thing they call a health screening that our insurance requires us to do. Otherwise, we have to pay more premium. It's the Public Education Employees Wellness Program screening, health screening. So I've got to do this. The time that it's on this campus is from 9 this morning, which has already started, until 1 this afternoon. Well, I'm in class here until 11:10. And I've got another class starting at 12, so the only time I've got in between is from basically 11:15 until 12. That's usually when I eat lunch, but it doesn't look like I'm going to be able to eat lunch today, or at least during that time. So I've got to go down there as soon as class is over with. So where I normally have office hours from 11:15 till 12, today they probably won't be that full time. Hopefully I can get the screening done in a fairly short amount of time, and then maybe get back to my office a little bit before my 12 o'clock class. So don't look for me in my office. Of course, you won't hear this until after this is all over with. Okay, but not only that. In addition to that, normally I have office hours on Mondays and Wednesdays from 3:15 to 5:15 in my office here on this campus. Not today, because today I've got to go to the Birmingham campus just about as soon as I get out of my 3:15 class, okay? I've got several things I've got to take care of. I've got to arrange a vehicle for Friday, and I'll talk about that in a minute. Possibly a vehicle for tomorrow. I don't think we have to do that. I've got to get the leave sheets done today, and I've got to get 2 ways of leave sheets and also some transportation requests. So I've got tons of stuff that I've got to do, so I've got to get out, and then I've got to work on the summer schedule as well. So I will be leaving campus almost as soon as I get out of my 3:15 class, and I'll have office hours, but they'll be on the Birmingham campus from whenever I get there, 3:45 or so until 5:15 or later. I'll probably be there later than that because I've got so much I need to do and cover. Okay, so that's today. Tomorrow, depends on what I found out from the transportation today, I might need to run over to the Birmingham campus. Normally, office hours on Tuesdays, Thursdays are 10:45 until 12:30. It looks like tomorrow I'll probably have to go to the Birmingham campus as soon as I get out of class at 10:45 and go over there and pick up the keys and stuff for the vehicle that I'll be taking on Friday, and I'll get to that in a minute too. There may be an outside chance I have to get a vehicle for tomorrow as well, but I haven't heard back from the people, so I assume that's not going to happen. So there's that. All right. Now, so my office hours are, at least a lot of them will be shot tomorrow, 10:45 until maybe I hope to be back before 12:30, but it won't be very long before 12:30. Okay? Then on Friday, normally I have office hours from 7:45 until 1. Last Friday I had my infusion, so I had to be at the Kirkland Clinic by 6:30, and I didn't leave until after 4:30, so I wasn't on campus at all last Friday. This Friday we'll be leaving at 6 and getting back around 6 because we've got math meetings down in Opelika at Southern Union State Community College, so we will be not on campus except right around 6 in the morning and right around 6 in the evening. None of my office hours I'll be on campus. So tomorrow my office hours are shot. And then one more. This is coming up next Friday, not day after tomorrow Friday, but the following Friday, I have my annual physical at 8 o'clock in the morning. So I won't be on the Birmingham campus at 7:45. I'll be at the Kirkland Clinic, and hopefully they'll finish the physical by 9 o'clock, and if so, then I hope to be back to the Birmingham campus by 9:45. So figure 9:45 to 10 o'clock, I'll be my office hours starting next Friday, and I'll be there at least until 1 o'clock. So lots of changes to office hours. I want to make sure you had a chance to hear most of those. Well, yes. I was tired of talking to myself, so I'm glad you showed up. Okay.
So quick question.
Okay.
Quick
answer. No.
Yeah.
Okay. Yeah.
Hidden figures.
Okay.
Are we going? Are we not going?
I am guessing not. I saw an email from Dr. Thomas this morning that you're the only one signed up.
Right.
But then Cameron came in and said he wanted to go, but he had a dentist appointment, but he thought he could change that. But yesterday afternoon, late, and I didn't get to see Dr. Thomas afterwards because she was already gone by the time I finished class. The phone call came in while I was in class. I just happened to hear it and took it. I was expecting a call from somewhere else because I had put in a couple of phone calls. So it was actually my boss saying that that we were trying to get the summer schedule finished. I had good progress on it, but not through. And I got to go to the Birmingham campus this afternoon at 3:15. So I can't be there at 3:45 today. I might be able to do a later showing, but not 3:45. And I think she had arranged everything for 3:45, but I didn't get to talk with her because of that. Now, I'm still open for later. We can't do it Friday because we're going to be in Opelika. Saturday would be possible. I can't do it early Saturday morning, but later in the day would be possible.
Okay. Well, I know the email said like a definitive answer would be at 12. I just didn't know.
Okay.
You know,
I haven't. When I got in this morning, Dr. Thomas wasn't in, so I couldn't tell her. I've been in class ever since, so I haven't gotten to tell her that. I think I know the definitive answer now, but now in my trig class yesterday, one of the students said she couldn't go, and another one said she would like to go, but evidently she hasn't communicated that to Dr. Thomas yet. But that was before I knew that I couldn't go today. All right, so I've got you here today. Okay, good deal. I don't know where the others are, but glad you're here. And I was just going through the announcements, and you'll have to listen to those once they get up on this. I hope you know about Financial Aid Awareness Week and homecoming, all the activities for that. That would have been announced had anyone been here. And then Miss Williams from Financial Services gave me a whole stack of things to tell students about. You're certainly welcome to look at any of these too. Okay. One of the things was for scholarships for government employees or government something in office. And when I was reading it to my first class, I got down to the third point requirement, and it said you had to be at a 4-year school. I don't think we qualify then. So I took those back, but she wasn't in her office, so I couldn't find out. All right, anyway. Any questions on calculus before we get there, or any other thing? Okay. We're on in section 3.2, page 122, and we're talking about differentiation and derivative as a function. And we're getting ready to do example 2. Okay? This figure that you see here was from example 1. We've already done that. There is no figure for example 2, so I will write on the same one. So it says, prove that y, whoops, let me get my pen darkened, okay, that y is equal to x to the minus 2 is differentiable and calculate y prime. So first we got to show that it's differentiable, okay, and then secondly, figure out what y prime is. Now,
It's
when I was talking to myself, I used that on the projector, and the lights on, I'm doing better, but reversing. Okay, so that should be coming on fairly quickly. Well, fairly soon. I won't say quickly, but soon. Now, I think I wrote down the problem wrong. It's x to the minus 2. X to the minus 1. Now, time out. How is another way you could write this? Y is equal to x to the minus 2.
Is that where it's 2 over x?
No, 1 over x squared. If you have a negative exponent, wherever that is, move it across the dividing line and drop the minus. Okay, so this would be x to the minus 2. Now, it says, the first thing it shows that it's differentiable. My question to you, are there any issues with that function?
Well, it can't be 0.
It cannot be 0. So everywhere the function is defined, with every place that it's not 0, yes, it will be differentiable. It's continuous left of 0 and right of 0. It's just not continuous at 0, so it can't be differentiable there. But everywhere that it is defined, it is differentiable. Okay? So that's the first part. The domain of f of x equal x to the minus 2 is a set of all x's such that x is not equal to 0. So we assume that x not equal to 0. So we assume x not 0. And we can compute f prime directly without the separate steps. Okay? So what is our definition for f prime then? So far. There will be an easier one later, but what's our definition so far?
Is it looking high or no?
No. Our definition. We haven't gotten there yet. Okay. The limit, and there's two ways you can write it. That's what I'm...
Oh, as h approaches...
Okay, you could do it as h approaches 0 of...
I forget.
Basically, difference quotient.
Right, so... Is it h minus 0 or no?
Okay. Is f of x plus h minus f of x over h, just over h. Got it. Okay? The change of the y's, f of x plus h minus f of x, divided by change of x's. X plus h minus x, that would be x minus x is 0, that would just be an h. Okay. So now, basically what we've said is that f of x is equal to x to the minus 2. Okay? We were calling it y, now we're going to call it f of x. Okay. So what's the first thing we've got to do to plug into that? Well, no, that's what we're trying to do. F of x plus h. We've got to figure out what that is. And what would that be then?
f of x plus
All right, no, okay. Everywhere you see an x here, we put an x plus h instead. So the x there is x to the minus 2, so this will be x plus h to the minus 2. Okay? So that's your f of x plus h. So that's we're going to plug in. Now I just assume not write the limit over again. Understand it's there. Okay, so f of x plus h is x plus h to the minus 2 minus x. Your f of x is x to the minus 2, and this is all over h. All right? Now, when taking derivatives, I really like to have an exponential form. But to simplify this, I really need it in rational form. So let's rewrite that as 1 over isn't that the same?
Okay, yeah,
X plus h to the minus 2 is that. minus 1 over
x
squared. And that's over h. Okay? Now, I've left off the limit. I'll go back and put in that later. Okay? Now, we got to fiddle with that numerator. Okay? What we have are fractional forms, different denominators. What do we have to have? Common denominator. What would that be?
x plus h
Squared times x squared. Okay? So we're going to have to multiply this by x squared and this by x squared. And over here we got to multiply by an x plus h squared. So this will be multiplied by x plus h squared. Okay, let's fiddle with what we got there. We got our least common denominator now, so I'm happier with that. But the numerator is now x squared minus, now we got to expand our x plus h squared. What would that be? X squared plus 2xh plus h squared. Now that in parentheses, because the whole thing is divided. And this is divided by x squared times x plus h squared. I'm not going to expand that. We'll just leave that like that. And that's all over h. Okay. Now, I'm going to come over here. And we're going to distribute the minus sign across the parentheses. So it's x squared minus x squared, right? Minus 2xh minus h squared over x squared times x plus h squared over h. Okay, what do you notice can happen in that numerator? X squareds add to 0. Okay. Now, what's remaining in the numerator there has a common factor of h. So factor out an h, and that gives you a, in fact, let's factor out a minus h. Why not? Okay. Somebody's coming in, maybe? Yes. Okay. Here is Nicole. And since you won't get to hear it, I put it on Screencast-O-Matic, but it won't be loaded by the time you'll need to hear it. Let me go over quickly for you. My office hours are kind of shot for part of this week and next week. Here's what they are. Normally I have office hours right after this class from 11:15 till 12 o'clock. That's usually when I eat too. However, today, and I didn't tell you this either, today we have a health screening for employees. We have to go to it or else they say our insurance goes up. Okay? So it's sort of mandatory unless you want to pay more for premiums. So, and it's only today from 9 until 1. Well, I have this class up until 11:10. I have another class starting at 12. So the only time I can do it is between 11:15 and 12 o'clock.
What is it?
They just do blood pressure, pulse check, diabetes check, cholesterol check, and they go through things. They take blood pressure, they do that kind of stuff. I guess what the deal is, they figure if they alert you to problems you might be having, you can take care of them before it gets too expensive. If you don't do it, then they could be expensive. They have to pay more, so they want to charge you more.
And I bet our nursing students get a chance to actually,
No, they bring in people. Now, the school nurse, Miss Gwendolyn Collins, is actually in charge of it, but they bring in, yes, it's Blue Cross Blue Shield has a team that comes around and does it. Okay. Yeah, it would be nice if they got to practice, but they don't.
That's what I thought.
Yeah. So what we're doing is example 2, bottom of page 722. Oh, that was just the first of it. So my office hours at the end of this class before the next class pretty much shot. Okay, I might get back to the office a few minutes before 12, but it won't be very long. Hopefully I'll have 15 minutes or so, maybe. Now, also I normally have office hours today, 3:15 to 5:15. But several things are happening. Number one, I may be taking, I'm hoping to take my physical science class on a field trip, and I called the people yesterday. They haven't got back to me yet. They said they're going to send me an email yesterday, They didn't. Okay, so I don't know if they're going to say come tomorrow. If they do, then I've got to arrange transportation. But whether I do that or not, I'm also taking a vehicle to Opelika on Friday, which is coming up later too, as part of the problems with my office hours. So I'll get to that later. So I've got to go to the Birmingham campus as soon as I'm out of my 3:15 class. I've got to go over there and do all, complete all the paperwork that I need for the trip on Friday. Okay, so I will have office hours, but they'll be on the Birmingham campus, not this campus. That's why I can't go to Hidden Figures, because I got to do that. Okay, so that wipes out my office hours on this campus, so I'll be over there. Then on Friday, like I was saying, we've got math meetings down in Opelika. We'll be leaving at 6 o'clock in the morning and not getting back until about 6 o'clock in the evening, which means no office hours on Friday. I was out last Friday because I had an infusion, and I'm out this Friday because of this trip. Okay, then even next Friday, I have my annual physical, okay? And so I have to be at the Kirkland Clinic probably by 7:45. My appointment's at 8, and hopefully I'll be through by 9, so hopefully I'll be back on campus by 9:45 or 10, but I can't guarantee that. Depends on how things go with the appointment. Usually they go pretty quickly. So my office hours are just really messed up the rest of this week and the end of next week. But other than that, it should get back to normal, whatever normal is. Okay, so I wanted to let you know that. I put that on Screencast-O-Matic, which will go to YouTube, but by the time 11:15, it's not going to be there yet. Okay. All right, so we're in the middle of this problem. We were just factoring out a minus h, leaving us a 2x plus h. Now, actually, I probably shouldn't have factored out the minus. I'm going to leave the minus in there. You'll see there's a reason for that coming up. So let me leave the minus signs inside the parentheses. Okay? Over x squared times x plus h squared. Okay? And that's all over h. All right. Now, I don't know if this is fair to do or not, but you see this h and that h can divide away. Okay? So what do we have? And now we're going to go back and take the limit as h is approaching 0. That was our first limit there. Okay. So with that h disappearing, we lose the h in the denominator, so we can proceed. So what we have now is minus 2x in the numerator there, okay? And down here we have an x squared, but then if h is approaching 0, this is just going to x, and that'll be another x squared. The pen is really slow right now. So there's the limit. Well, let's clean that up a little bit. That would be a minus 2 over, there's x up here, x fourth down here, that would be x cubed. So let me rewrite that as minus 2x to the minus 3. Okay. You don't have to do it that way, but that to me is the cleanest way. So there is the derivative, y prime of x to the minus 2. Okay. A little bit later we'll say, oh yeah, we could have done that in one step. Okay? We haven't gotten there yet, but we got it. Okay? Minus 2, x to the minus 3. The limit exists for all x's not equal to 0, so y is differentiable, and y prime is that amount.
Oh my goodness, we could have done that in one step.
In one step, exactly. But we haven't gotten there yet. Okay?
Yeah.
But this shows that it does work. That step does work. Now, things to note there. Okay? I'm going to basically draw this function here. Okay? it's going to look something like this and something like this. Okay? Now, the reason I did that is to show when x is less than 0, x to the, this could be written here, x cubed is negative, right? And this is negative. 2 is negative, and x cubed would be negative. So this would be positive. And sure enough, on the right side, for all x's negative, you have a positive slope. For all positive x's, this is positive, that's negative, and for all positive x's, you have a negative slope. And sure enough, you have. It's increasing here, decreasing there. So just to give you a hint, yeah, this is making sense. It does. All right. Now, they do a little bit of a jump here, and I guess it's justified here. They have a little bit of a blurb on Gottfried Leibniz, I think is how you pronounce it. I used to always say Leibniz, but I think I've seen somewhere it's actually pronounced Leibniz. Yeah, right here. This is where it says. Gottfried Wilhelm von Leibniz, okay, 1646 to 1716, was a German philosopher. And by the way, he only lived, what is that, 70 years, right? Okay, German philosopher and scientist. Newton and Leibniz are often regarded as the inventors of calculus, working independently. Now that's where the big rub comes. It is more accurate to credit them with developing calculus into a general and fundamental discipline because many particular results of calculus had been discovered previously by other mathematicians, but it was all sort of scattered in not one particular field.
Is this the guy that you were talking about that him and Newton kind of did, like they wouldn't even consider, they were trying to like out-publish one another?
Well, yeah, kind of. What happened, Newton had been working on what he called the method of fluxions. That was his name for it. That means flow, change, and stuff like that. Mm-hmm. And he had his own peculiar notation and did lots of things with it. But Newton was a perfectionist, and he had been working on this, collaborating with others, and had communicated with Leibniz, okay, some of his ideas. Well, Leibniz turned around and, according to Newton, took those ideas and pursued them independently, but having gotten the idea from Newton and rushed out there and published first. Newton was slow to publish because he didn't want anybody to doubt. He didn't want any questions. He wanted all the I's crossed, or the T's crossed and the I's dotted and that kind of stuff. He didn't want any objection. Leibniz wasn't that careful. Okay, he was good. He was a great mathematician, great scientist, good philosopher, all that kind of stuff. But he and Leibniz then went at it for almost the rest of their professional lives, just bickering with each other who had plagiarized whom. Leibniz did publish first, but it was well documented Newton had started first, and that's where the big problems came, okay? So, definitely a lot of paper topics here. Leibniz himself, their feud, what they did, other people who had contributed before them, lots of potential paper topics there. Why we're mentioning him now is the fact, and by the way, he lived to be 70. Newton lived older than that, and I think outlived him. Not by a whole lot, but by some. I can't remember how old Newton was when he died. But anyway, it was just incredible that these two incredibly talented mathematicians came along at the same time and did the same thing. Groundbreaking, whole new field of mathematics at the same time. Well, the prime notation that we've been using was first introduced by French mathematician Joseph Louis Lagrange. He's quite a mathematician himself. He's a potential paper topic. He came along 1736, so he was born 20 years after Leibniz died and lived till 1813, almost 100 years after Leibniz died, okay, he came up with the prime notation. It is pretty neat and handy and short, but Leibniz had this notation. Oops. All right, they're skipping a lot of steps here. Wow. Okay, yeah. This slide set is from my CD is from the previous edition, so it doesn't have everything this does. But I'm going to fill in the gaps here. Leibniz used this notation, df dx, okay, or dy dx. But remember from pre-calculus, f of x is equal to y. So this is basically saying the same thing. Okay, so this was Leibniz notation. It comes from the concept of a delta f over delta x, which basically is your difference quotient. Change of f over change of x. F of x plus h minus f of x over x plus h minus f of x, change of x. And same thing here, delta y over delta x, which basically is your slope of a secant line, okay? So that's where, and you see, these kind of things Leibniz did independent of Newton. So, but still the concept, Newton claimed was his. Leibniz may have prettied it up some, but yeah, but that was the whole debate. Okay. In Leibniz notation, whereas before we said y prime was equal to minus 2x, here we would say dy dx is equal to minus 2x to the minus 3 from that last example. It's just a nomenclature. Now, what if we were wanting to evaluate that at a specific value? Now, in the prime notation, we'd say y prime at, say, 4, and we just plug in the 4 where the x was. In this notation, we say dy dx, okay, when x equals 4. Same thing, and you'd plug it in just the same way. Here it would be minus 2 times 4 to the minus 3. Here we would be minus 2 times 4 to the minus 3. It doesn't matter which order you do the thing. There's no difference between this and that. I just wrote it differently. Okay. Or df dx at x equals 4. Okay? And that would be minus 2 times 4 to the minus 3, or wherever you put the exponent. Okay? Now, these symbols here we call differentials. And it really makes, especially in the next, when you do integral calculus, and then when you do Cal 3, and when you do differential equations, even though this looks like that's a quotient, and in this form and that form they look like quotients, they are quotients, are difference quotients, okay? But when you write them in the D form, not the delta form, they're no longer quotients. That is a symbol, dy dx. But when we write them as differentials, we can separate that and do the dy on this side and the dx on that side. That's called differential notation as opposed to derivative notation. So it's a little murky there. A lot of times we treat them almost as if that's a quotient. Keep in mind it really isn't. That's an operation, okay? So the dy and dx are differentials. So conceptual insight here, Leibniz notation is widely used for several reasons. First, it reminds us of the derivative. The knot itself is a ratio, is in fact a limit of ratios, delta f over delta x. Secondly, the notation specifies the independent variable. The thing on the bottom is the independent variable. If you have a variable on top, that's a dependent variable. Okay? That's useful when variables other than x are used, okay? For example, if the independent variable is t, then we write df dt, okay? Whatever the independent variable, that's on the bottom, okay? Now, what I was saying before, we think of d by dt or d by dx as being the operator, and you operate either on function f or on function y or whatever it is, but really what goes here is what you're operating on. The rest of it is the operator, okay? Even though you write it like this is what's being operated on by this operator here, okay? That was ugly symbol, okay? All right. And then there'll be other advantages of Leibniz notation when we get to the chain rule, which is coming up in 3.7. Now, the main goal of this chapter is to develop basic rules for differentiation, okay? These rules enable us to find derivatives without computing limits. I'm all in favor, okay? For example, in theorem whatever, and there will be several of them, of the previous section, why do they do that? I thought they were referring to the theorems coming up here, but in the previous section, why do they put question mark, question mark? That's bizarre, okay? Evidently someone had intended someone to go and fill in the blank there, but I think it's theorem 1, because they only have one thing there, okay? Yeah, so why in the world that's question mark, question mark? Duh. Okay, we stated the following fact in slightly different notation, okay? The constant rule. Now it's going to be our theorem 1 in this section as well. D by dx, or whatever your variable happened to be, of the constant function c, what do you reckon that is?
I
Huh?
peeked ahead.
Yeah. Well, the constant function c is a function that's always constant. Always value c. How is that changing as x changes? It's not.
Yeah.
It's always c. So the change of c for change of x is 0. Okay? Because the constant function isn't changing. And that's what you're measuring here, change of the function per change of x. If it's not changing, if you have no change of y, then, and you don't, if it's a constant c, this is always 0. So that was theorem 1 in this section. That was included in theorem 1 of the previous section. Okay? Now, if you did the definition of a limit, it's pretty easy to do. That'd be the limit as x approaches, no, we're using h approaching 0 of f of x plus h minus f of x over h, where your f of x is equal to c. F of x plus h. Guess what that is? It's c also. It's a constant. So this would be c minus c over h at 0. Don't have to get rid of the h there. The numerator goes to 0. The limit goes to 0. Okay? So that's done. Now, also in that theorem 1 of the previous section, and they just sort of showed these, here is theorem 2 in this section. It was A and B in the previous one. It's two separate ones. What is derivative with respect to x of the function x? One. Okay? I mean, even if you wrote it, dx, that looks like that's got to be 1, and it is. Okay? That you aren't supposed to think of it that way. You're supposed to think of f, the limit, as h approaches 0 of f of x plus h minus f of x over h, where your f of x is equal to x, and f of x plus h is equal to x plus h, right? So this would be x plus h minus x over h. 1. Yeah. So, for sure that's the case. Okay? I think we just did the proof there too. Yeah. All right. So then let's move on to the power rule. That's the one we've got here. So let's highlight this or zoom in on it. Here is the product rule. And this is what we were just doing, whether you realize it or not, in the earlier examples. If you're taking the derivative of a power, x to the n, here's the rule. Exponent times coefficient, n times 1 is n, times x to the drop the power by 1, n minus 1. That's what we have for all exponents n. Now, I want to just, that last problem we did, yuck, was find the derivative of x to the minus 2 dx. Okay, let's use this rule. Your exponent's minus 2, your coefficient's 1, so that'd be minus 2 x to the, and it would be minus 2 minus 1 would be minus 3. That's what we got after all that ramification of, least common denominator subtractions, canceling, dividing, stuff like this. We wound up there. We could have done it. Had we known the power rule already, written it down. Done. Okay? Now, they go about a way of proving it, and their proof is pretty, in a little way, a little complicated. They have to show you a pattern.
Jeez.
Yeah.
Oh.
Yeah. Anytime you have x to a power minus a to the same power, you can always factor that as x minus a times something else. Now, the bigger the power, the bigger and the messier that something else is. But you can always factor out the x minus a. And that basically is what they're going to use with this. And it is a long, really hairy proof that I don't think we have time for. Well worth a read, though. Okay?
I'll take your word for it.
Okay. Thank you. Okay.
And yours. How about that?
Yeah. Okay. So we'll move on from there. In words, I've already been saying the words exponent times coefficient. They don't mention the coefficient yet, but it's true. Exponent times coefficient times x to the drop 1 power. Okay. Now, that's only good for power functions. Y is equal to x to the n. Does not apply to functions like that, 2 to the x. You can't do the power function there. That's not a power. That's an exponential function. It has a whole another set of rules. Okay? So don't try to do that. Don't try to do x times 2 to the x minus 1. That's not going to work. So don't even do it. I even regret they did that. Okay. They do a few more examples, so let's do a few of those. D by dx of x to the minus 3/5. What would that be? Negative 3/5. That's the exponent times coefficient of 1 times x to the negative 8/5. Subtract a 1, but since you're dealing with fifths, subtract off a 5/5. That's 1, and that would give you minus 8/5. Very good. How about, can you even do this? D by dx of x to the square root of 2. What would that be? The square root of 2. The square root of 2 minus 1. Now be sure that square root ends at the 2. You don't extend it over to the minus 1. That's exactly. Okay? How about d by dz, they're calling this time. You can have anything as an independent variable of z squared. What would that be? 2z. Done. Z to the first. How about d by dt? You can have any independent variable of 20 t to the 19th. Can you do that?
Yeah, 19 times 20. 380.
380.
Sorry.
T to the 18th. Wouldn't you rather do that by the limit rule? Please not. Okay. You like this much better. Okay. There we have it. Okay. I messed up. Sorry about that. I was reading the wrong thing. That was supposed to be d by dt. I was looking at the answer, not the problem, of t to the 20th. Okay. And that would be 20 times t to the 19th. Much easier problem. I messed up in my reading. But what we just did is right. Yeah.
My thing about it, though, is the limit, like, dealing with limits trips me up all the time. Doing this stuff, it kind of eliminates a lot of the pitfalls you can fall into with dealing with limits.
Right.
Having to transform equations and stuff. And I know that that's going to be important, but it's like, I don't know, having this shortcut really helps.
Oh, yeah.
Cut out a lot of the mishaps that can go on between starting and finishing a problem.
Right. But you're not speaking as a true mathematician, are you? Okay. Mathematicians are supposed to love the theory and the limits and stuff. But, yeah, you're absolutely right. Let's do one more. It's not much different. D by dr. And we've got Rodney here. 3 out of 4, just missing Samaria. Okay. D by dr of, let's write it down right now, r to the 1/2. What would that be? 1/2 r to the negative 1/2. Now, and they just leave it like that, which is perfectly fine. You could write that, and this is only if you just prefer it this way, 1 over 2r to the 1/2. Again, if you have a negative exponent, move it across the dividing line. That's the same answer. So, but I like negative exponents fine. All right, next we get to the linearity rules. Okay, no, we don't. No, this is part of the proof of the power rule. Remember, this was the power rule. Here was part of that proof that we're not doing, but I will show you since they did a slide on it. Okay. This is just a truth here. X to the n minus a to the n, where x is a variable, a is a number. As long as those are raised to the same power, then you can factor out 1x minus a, and what you have left is, if you divide this into that, you get x to the n minus 1, then multiply, and you bring down you can do the division and see what you get. And notice what happens. Your x's decrease in powers. Is n minus 1 to n minus 2 to n minus 3 to n minus 4, while the a's are going up in power. A to the 0, which is 1, a to the 1, a to the second, a to the third, fourth, up until you get, and a goes right up to n minus 1. X's start at n minus 1 and go down. A's start at 1 and go up. And that's what you get. It's kind of a binomial expansion type thing. Not quite the same, but it's very similar to it. One power is going down while the other power is going up. And you can prove that, multiply through and you see that's what you get. I'll just take a few terms to show it. Let's do this one times this one, that'd be x to the n. There you have it, right? Okay. Then let's do this one times this one. That gives you x to the n minus 1 times a. But when you multiply these, you get minus a times x to the n minus 1. They go away.
Can we plug something in just to kind of give us some numbers to look at? Like with x to the something minus a to the something?
Okay. And you want A plugged in a number there, or leave that A?
Oh, nothing plugged into X or A, just something plugged
For
into the
N.
ends. Yeah.
Okay. All right.
Just to kind of give us a visual.
Give me an N.
How about 4 on both?
Okay. Let me see if I can get this one. Okay, here we go. Okay, X to the fourth minus A to the fourth. Okay. According to what we just said, this would be X minus A times cube, just X to the cube, okay, plus X squared A. What's that? Is N minus 1. We pulled out X minus A. Pulled out one of the X's, that leaves X cubed. Okay? And then X squared A plus X A squared plus A cubed. You got it. Okay?
Okay. Gotcha.
That's what it means. The X's are going down, the A's are going up.
Cool.
Now, check to see if that makes sense. X times X cubed is X to the fourth. That's good. X times X squared A would be X cubed times A. But here we have a minus X cubed times A. That's why those terms go away. Next one we'd have X squared A squared minus X squared A squared. Those go away. And then you'd have a X A cubed minus X A cubed. Those go away. And then you'd have a minus A fourth. And that's there.
Okay. Cool.
Okay. And that works for any N, not just for any N. Okay. Now, if you remember, don't know if you do, I don't know if you chose to, when we did X cubed minus A cubed, difference of two perfect cubes, what do we say that was? X minus A times, and I gave the little rule, if you were in my class, square the first, the product, opposite the product of the two, plus A squared. And that follows the same pattern here, isn't it?
Yeah.
See that all pluses here, this is going down, this is going up.
That's right.
So that, back then we didn't have this rule, so I made up a little rule, okay? But that works. Now, it also works for X cubed plus A cubed. That doesn't work up there for higher powers, I don't think, okay? I haven't investigated it anyway. Okay. So, okay. That was part of the proof that you're going to pursue later. So, if you go through the proof, that was the first step. And then the next thing we do, notice here, I'm going to erase what we've got here. Okay. The next step they do is divide both sides by X minus A. So this goes out here and you're left with that, and that gives you this step. X to the n minus A to the n divided by X minus A is that n terms that we had left over, right? Okay. For the cubic, that would have been, if that was to the fourth here, that's been your X cubed plus X squared A plus X A squared plus X. You would have had 4 terms because we had n to begin with 4. So, now, the thing that you can't have is X equal A. And X can't be A because it messes up then. Okay. Undefined. But you could let X approach A, which is what we're going to do. Okay. Now, this is the rule then we had at the bottom of the page. After they proved everything, this is, they said it in words. D by dx of x to some exponent will be the exponent times x to the exponent minus 1. And then we did several examples with that. Okay. All right. That leads now to the linearity rules. Now, in this edition, the older edition, this is theorem 2. Of course, in your book, it's theorem 4 because we had theorem 1 and 2 repeated from the previous section that they didn't do in the old edition.
Real quick, I'm sorry, before you
Yeah.
move on, did that cover what you were talking about with the issue? I think it was that whenever you had like 2 to the x, I mean that was, we covered that with the exponential or exponent thing.
Right.
Correct.
Okay, no, that still doesn't apply
Okay,
here.
so
Right.
we'll deal with that
Yeah,
later. Okay.
we'll get there, and I think later in this chapter, but it's going to be a
Is
while.
that the chain rule?
Not yet.
Yeah.
You see, that kind of function is called an exponential function. These are power functions,
Yeah.
are the ones we were just doing. Power functions. Power function and exponential function look similar, but they're not.
Okay.
With the power function, your variable is the base, and you have numerical exponents.
Right.
In an exponential function, you have a numeric base, and the variable is your exponent.
Right.
So they look similar, but they're very, very different functions. Okay. Different rules of everything. We'll get there. Linearity rules. Assume that f and g are both differentiable functions. We don't know what they are, but let's assume they're differentiable. Then, the sum and the difference rules. If you have a sum of the two functions, that is a function. And then, because both of them are differentiable, the sum function will also be differentiable. That's the first part here. And what's more, the derivative of the sum is the sum of the derivatives. Okay? That's the linearity rule. The derivative of the difference is the difference of the derivatives. Another linearity rule. And then the third linearity rule, though those two are usually written as one, is the constant multiple rule that for any constant c, remember f is differentiable, c times that f is also differentiable, and what is its derivative? It's c times f prime. Okay? In other words, the constant can be pulled out and just take the root of the functions. Okay? Now, with the power rule, which we just did, and these linearity rules, sums, difference, and exponents, coefficients, now we can extend it to any polynomial function. Because what's a polynomial function? A sum or a difference of various power functions. So we can extend that, and they may have coefficients. So this enables us to do any polynomial. Now, they have a proof of the sum rule, which is perfectly fine. It's fairly easy to follow, so I suggest following it. It's just we don't have a lot of time, so I'm not going to. It's not that bad. Okay. That doesn't sound very positive, does it? All right, let's move on to example 3. All right. Find the points on the graph of f of t is equal to t cubed minus 12t plus 4, where the tangent line is horizontal. And this is shown in this figure. Okay? Well, how do we do that? Okay. Now, yeah, exactly. Take a derivative, okay? And let me get back down. So let's do, with this as our f, what is our f prime? Now, if you preferred the f dt, that's fine too. Whatever, it's just easier to write this. What would that be? 3t squared, that's the power rule. Then the sum and difference rule say subtract. Minus 12. All right, that's it. Okay? Now, the question was, find the points on this graph where the tangent line is horizontal. Well, how is a tangent line related to the derivative? Why did you have me do a derivative?
Because the slope of the tangent line
is the first derivative.
Yeah.
Okay? Now, they say where the tangent line is horizontal. What can you tell me about the slope of a horizontal line?
It's constant.
So the line is constant. What's the slope of it?
Whatever it's no.
What was that theorem 1? This section.
In this section, the constant rule is so whatever the constant is, so whatever you plug it in.
What is the derivative of it? Read that a little more carefully.
Zero.
Zero. The derivative is zero.
Yeah.
So if you're saying where is the okay. Where the tangent line is horizontal, a horizontal line is a constant function, and the derivative of a constant function is the derivative of a horizontal line is zero. So we set this equal to zero. Oh, that's the slope of your derivative. So we set that equal to zero. Okay?
So add 12.
Add 12 to both sides. Okay? That gives you 3t squared is equal to 12. Divide by 3.
4, or t squared equals 4. Take square root, and then you're left with t equals 2.
Plus or minus 2. Anytime you take the square root of both sides of an equation, you've got to include the plus and minus. So that's why the tangent line at t equals plus or minus 2 are horizontal, because the slope of the tangent line is 0. It's a horizontal line. But that's not what it asked for. It said, find the points on the graph of this where the tangent line is horizontal. You plug this in here. So f of 2, we'll do the 2 first, is equal to 8. Yeah, 2 cubed is 8. Plus, oh yeah, I forgot this is plus 4 there. And that's equal to? Say again?
Is that 20? No, excuse me. 12.
12. Okay. So one of the points will be at, yeah, okay. They really have a strange looking graph here. This point is, oh, that's a minus 12. Yeah, okay, I was going to say. This point is at 2 minus 12. And the other would be f of negative 2 would be, plug in here, negative 8 plus 24 plus 4, and that would be, that adds up to 28. Yeah, 20. Okay, got it. Sorry. A little on the slow part. Yeah, okay. So this will be at the point negative 2 comma 20. So down here, minus 12, up here, plus 20. Yeah. Okay. Those are the points. That answers the question. Okay. The question said, find the points on the graph of this function where the tangent line is horizontal. Okay. X equals plus 2 and minus 2, but you plug that in here, and you get the points on that line.
I see how they numbered the number line now.
Yeah.
Vertically.
Yeah.
But on first I was like, so it's 0.40. Why are they making such? Because
Yeah, because this is such a huge scale. Well, I mean, this is a cube. Yeah. So
right.
It's going to expand really greatly. If they put it on the same scale as the X, it would be way tall, and this would be really crushed here. So yeah, that is exactly what's going on. They did modify the scale. They compressed the Y scale and expanded the X scale. Okay. Any questions on that? All right, let's do example 4. Okay. Let's see, I don't think they have a figure for example 4, so we'll do it here. Calculate dg dt at t equal 1, g of t oh, 2 square root of t. I'm listening, not reading, so sorry. I thought you said t square root of t. Okay, no, my bad. 2 times the square root of t
minus t to the
minus 4/5.
Negative 4, yeah. You got it.
Okay. Now, weird the way they wrote this. Okay. Two of the things are exactly like they should have written it. One of them is not. Okay. Now, of course, you could have written this as 1 over t cubed. Okay. Please don't. Okay. Keep it in exponential notation. This one they wrote in radical notation. Please don't write that in exponential notation. This one you could have written in radical notation. That would be in a minus 1 over, because of the minus sign there, the 5th root of t4. Please don't, okay? Write it just like they did here in exponential notation. Even though you have negative or fractional exponents, it's far easier to take derivative of these than it is that. Okay? So, first thing we do is write that middle term in exponential notation as well. So this will be t to the minus 3 plus 2
Is that t
to the 1/2 power, the square root of 2. What the index of the radical is, that's your denominator, and what the exponent of the variable is, that's the numerator. So that doesn't have, it just has an exponent of 1, so that's 1 over 2. Now, anytime you see a radical without an index, assume it's 2. Any other radical, if it's any other root, it's got to have the index in it. So most of the time, if you don't see a number, you assume it's 1, coefficient or exponent. But if you don't see a number on a radical, you assume it's 2. That's the only time you make the assumption for 2. Okay? And then this is minus t to the minus 4/5. So now let's take dg dt of that. Don't worry about the t equal 1. We'll get there in a minute. Minus 3 t to the negative 4, always reduced by 1.
And then 2 and 1/2.
2 times 1/2 is
1
1 plus t to the negative 1/2. Did everybody see this?
And then so positive 4/5
Plus 4/5 t to the
9 over
negative 9 over 5. You reduce it by 1, and since it's in fifths, make that 5/5, and that goes down by 5/5. 4/5 minus 5/5 is minus 9/5. Okay, now, to me, that's perfectly fine to leave it in that form. In fact, I wouldn't want to change. Okay, but now let's evaluate that dg dt when t is equal to 1. Next to the easiest number to evaluate, this would be what?
-3 to the negative 4 over 4 negative 4.
But it's 1 to the 4th. Right?
Yeah.
Okay?
Sorry. And then that 1 over t to 1 to the 1/2.
The square root of 1.
1, right. Over, yeah. Right. And then 4t. 4/5 to,
The 5th root, 1 to the 9th power.
yeah. Sorry, I really.
But guess what, folks? 1 to any power is 1. Okay? So this just simply becomes minus 3 plus 1 plus 4/5. Right?
Yes.
Okay?
Yeah.
That's why I said the next to the easiest thing to evaluate is your variable equal 1. The easiest is the variable is equal to 0. That's even easier. Okay. Most of the time. Okay, so this will be what?
Negative 1 1/5.
Okay. This would be negative 2, and 4 plus 4/5 would be negative 1, and is that what you said? 1/5. Yeah, 1/5. Okay. Negative 1, or,
Is that right?
yeah, or negative 6/5.
Right.
That would be another way to write it. So you could write this minus 15/5 plus 5/5 plus 4/5. Okay, 4 plus 5 is 9. That would be minus 6/5. Yeah. This is fine to write it that way too. Let me clean up my writing there. Okay. That's fine to write it that way, but a lot of times the book will write it in improper fractions. Just seem to be a little easier. Minus 6/5. Got it. Now, I've already sort of snuck this in on you, but we could do it again here. This is talking about if you know how a function graphs, which you don't always, but sometimes you do, and if you do, you know something about its derivatives. Okay? This is a cubic function, right? What we already know about cubic functions, I hope you do anyway, they could have up to 3 zeros. This one happens to have 3 zeros. You won't have any more than that, so that means this is continuing to go down, that's continuing to go up. Okay? This is recalling Math 112. Okay? Your end behavior here, these are going in opposite direction because it's an odd exponent, but with a positive coefficient, that means it's going like this. And sure enough, it is. Okay. Now, that's all stuff we knew already. When you have an increasing function, you always have positive first derivatives. So the tangent lines are positive up to here, negative here because it's decreasing there. Notice all the tangent lines are negative there. The slope is negative. And once you pass this point, though, it's increasing again, so all your tangent lines have a positive slope. Okay? So basically, that lets you know where the function's increasing and where it's decreasing.
Right.
Remember, back in Math 112, you had to do a lot of guessing, plugging in numbers, and that kind of stuff. Now we can just look at the first derivatives and they can tell us. In between those places, where it's positive here, negative there, it's 0. Those are places where you have relative maximum or minimum. Or they also can have an inflection point. We won't go there yet, but that's also. And these are sometimes called the critical points. These are the places where you're changing your slope. It was positive, it's now negative. Right in between there, it had to be 0 somewhere. Same thing there. It was negative, it became positive, somewhere there it had to be 0. And those 0 points would be, if you had a change of slope, then they would be the maximum end, depending on what we were on the other side. Now, you can look at the graph and see that. Can you look at this and see it? Probably not as easily until you do what? Take a derivative. Very good. I hope people don't get offended with this, but occasionally I'll make the dumb joke. Sorry. Have you ever been in church when they have children's church or that kind of thing, and the pastor or the leader or someone will ask the kids a question, and there's always some kid that whatever the pastor asks, they're going to answer Jesus. Okay, so in this course, whenever it says, and what do you think you'll do next, is take a derivative. That's a good choice. It won't always be the right answer, but it's quite often going to be. So let's take a derivative of this. Let's do f prime of x. And what will that be?
3x squared negative 24x and 36.
Plus 36. Okay. What does that plot as? A parabola, exactly. Okay. And what are the features of that parabola? Where the slope of this is 0, the first derivative is 0. So So you can set that equal to 0 here and see where those values are, which is the same thing we did before. Set that equal to 0. And first thing you would do is what?
Or would you try to see if it will foil? Or, I mean,
Unfoil?
unfold, or,
I would, but not yet.
okay, so subtract 36 first?
I wouldn't do that either.
Okay. Would you take out a 3?
Absolutely. Divide out any common factors first.
Okay.
So that would be 3 times
X squared.
x squared
Minus X.
minus
8X.
8x
Plus 11.
12. 3 doesn't. Okay, right. That's equal to 0. Okay? Now, this looks like it's magic, but it's legal. Divide out a 3. And that gives you a 0 still. Now this one, I would try to unfold. X squared minus 8x plus 12 equals 0. Is that factorable? I don't know. Let's try it. X and X. Negative, negative.
6 and 2. 6,
Very good. So that would be x equals 6, x equal 2. Those would be the two places where there's x equal 2, x equals 6. Got it. And the graph of this, the graph of the first derivative, that would be a 0 here and a 0 there. Absolutely. Now, we also know, looking at this, oh, they did it down here, okay? Down here where they did it, you can see the coefficient is positive, and that means it's opening upward. Okay, remember that? Okay, this is on the up and up, because the positive coefficient, even exponent, got to go to the same direction with the even exponent, because the positive coefficient is going up. So sure enough, so there, for somewhere in between here, you have your minimum here. Well, what does that mean? Okay, that means I want to say it if I can. The derivative of this derivative is 0, which, by the way, is the second derivative. We haven't gotten there yet. And what that means is, I shouldn't be saying this yet. This is what we call concave down. This is what we call concave up. The point where it changes from going down to going up, curving down to curving up. That's the point of inflection. And that's where the second derivative is 0. But don't worry about that yet. All we're interested in now, the first derivative is positive out here, negative in here, going downhill there, and positive out here. Positive, negative, positive. Sloping up, sloping down, sloping up. And the places. All right.
Because what we did, it was negative 12x squared, and whenever we took the derivative of that, you bring down x and you multiply by 12. So negative 12 times 2 is negative 24x. Yeah.
Okay. All right. What I didn't realize, we were just doing example 5. Okay. How is the graph of f of x equal x cubed minus 12x squared plus 36x minus 16 related to the derivative f prime, which is 3x squared minus 24x plus 36? How are they related? Second cousins, twice you know. Okay. They are, when the slope of the first graph is positive, that means the second graph value is positive. When the slope is 0, that means the value of the second one is 0. When the slope is negative, that means the value of the second one is negative. And when the slope is 0 again, that means your value is 0. And then when the slope goes back positive, it's that way. So that's one way to look at it. There's several other things you can talk about, but that's most of it. Okay? they do a little table here. Property of f prime. If f prime is negative, that means your slope of your original function is the function is decreasing. Okay, and they show that there. That first derivative is negative between 2 and 6. Okay, f prime of 2 is 0. F prime of 6 is 0. We saw that at the very beginning. And f prime is positive anytime x is less than 2 or greater than 6. Okay?
I'm sorry, I gotta ask.
Yeah.
It's kind of bugging me ever since you said it. What were you talking about the second derivative with? Now, because I'm
Okay. Second derivative, you take a derivative of the first
right.
derivative.
Yeah.
Okay.
I took it.
Okay.
But what does that?
Okay.
Yeah.
What that shows you where that is 0, that means where you have what they call it is an inflection point. That's where your first derivative is decreasing and then increasing. Where that first derivative is 0, that means you change from where the first derivative is decreasing. Even if it's positive, it's getting less and less and less. When it's negative, it's getting more and more negative, right? But then when it changes and becomes 0, that then is when it changes from going downward to going upward.
Gotcha.
Okay? That's called an inflection point.
Gotcha.
But I shouldn't have said that yet.
Sorry.
Yeah. Okay, I think the next is example 6. So let's try. Oh no, this is the table showing the same thing I was just reading. I'll blow it up so we can read it better. All right. You got a function, f of x. Take the derivative of that function, f prime of x. Well, that f prime is negative. That means your function is decreasing. It was negative, this one we had here, negative between 2 and 6. That means the tangent line had a negative slope between 2 and 6, meaning it was a decreasing on that interval 2 to 6. F prime of 2 and f prime of 6. This is the first thing you would do, is find out the 0 points. Why they list that other? Yeah, I don't know. Find these first, and that's where the first derivative is 0, meaning horizontal tangent lines, which usually means a maximum or a minimum. Okay? Tangent line is horizontal at those 2 points. Now they don't have to be. We'll see some examples of where the first derivative is 0, but they're not maximum later. But we'll get there. Then you go back and see where that first derivative is negative, and that shows where the tangent line is a negative slope, versus the first derivative is positive. That means the tangent line has a positive slope. So that's what the first derivative tells you about the function. Okay? Analyze the characteristics of the first derivative. That gives you characteristics of the function itself. Okay. This is example 6, I'm pretty sure. Okay. Oh, I think I can get them all in one slide. I thought maybe I couldn't, but let's see. All right. Here we have the graph of f of x. Now, they haven't given us what it is, but there's the graph of f of x. Just looking at this, I would say that it's a quartic function, maximum exponent of 4. The reason is it looks like it's going up and up. You have at least 4 zeros and 3 turning points. So that looks like it's a quartic function. May not be. Okay. Let's read what the problem says. Identifying the derivative. The graph of f is shown in figure 5a. That's this one. Only, yeah, okay. Which graph, B or C, is the graph of f prime? What do you think? Frankly, I think the easiest thing would be to find the zeros first. Yeah. The first derivative would be 0 because there's no slope here. That's near x equal 1. Maybe exactly that. At x equal 4 and x equals 7. So it's better have a 0 at 1, no 0
So,
at 4.
C.
It does at 7. So it can't be B. How about C? 0 at 1, 4, and 7. That's looking better. Still don't know for sure. Here it shows this has a negative slope, so your slope had better be negative from 0 to 1. Sure enough, it is. Here it has a positive slope from 1 to 4. Sure enough, it does. Positive. Decreasing, increasing to begin with, decreasing later, but always positive. And then it's a negative slope between 4 and 7. Sure enough, the first derivative is negative there. And then past 7 is a positive slope from there on. And sure enough, the slope is positive. Fits on every count. C is the graph of your first derivative, not B. And frankly, first look for those horizontal tangent lines. Derivative's got to be 0 there. Make sure you find it. Okay? Once you got that, then look at the slopes of the other slopes. Yeah, you can confirm it. Remember, this is the negative slope of this. This is the positive slope of this. This is the negative slope of this. And this is the positive slope. It doesn't mean everywhere you have a negative slope, this function better be decreasing. Positive slope is increasing, not necessarily positive. It's increasing down here, though the value is negative. It's the value positive here, but the slope is decreasing. So you make sure you separate those two from the value to the slope. That is the value of the slope. This is the value of the function. Okay. And of course, pointing on the board, you don't see that at home, so it pays to be here. All right. This is the chart. They like these little charts that describes what we were just saying. The slope of the tangent line of the function itself, where the slope is negative, where was that? Yuck. If I go back and forth, I'll lose the blow up.
Hold on.
Yeah, so I think I will. Okay. Let's go back to this. Where the slope is negative, that's between 0 and 1. Okay? 0 and 1. Now, those are intervals there. Those aren't points. Remember, interval notation, they use parentheses to indicate the limits, So that is not the point 0, 1. It's the interval from x equals 0 to x equals 1. Okay? And then you go back here again. It's a negative slope from 4 to 7. And that's what it shows there. It's a 0 slope at x equals 1, 4, and 7. You see that at 1, 4, and 7. And that's where I would start. I always start with the 0 slopes and then back up and do the others. And then it's a positive slope. Oops, let's go back to this one. Positive slope from 1 to 4, and again from 7 on. And that's 1 to 4, and 7 to infinity. Now, you might ask, why do you say to infinity here, but you didn't say from negative infinity here? They show the graph here, but they don't show the line. They show the axes here, but don't show the line, which indicates this terminates there. So you go from 0 to 1 or whatever. This one, at the end here, this is still going up, so you assume that's going. All right. I think we're ready for theorem. Woo. In your book, it's theorem 5. On the slides, it was theorem 3, because they skipped the first 2 theorems in this section. They counted those as being covered in the previous section. Now we're getting to a little bit of where Richard was asking earlier. Except we're starting with a weird number. The number E. Now what is that number E? Anyone got an idea? It's the natural base of our number system. We might say we're a base 10 number system. In some ways we are, because we got 10 fingers, I think, is the main reason for that. That's just a guess on my part. But the real natural base of our system is this number E, which happens not to be a rational number at all. It's an irrational number. 10 is a very rational number. E is not. There is a unique positive real number E with the property that the derivative of the function e to the x is the function e to the x, okay? Now this seems a little bizarre to be doing to you right now. The number e is irrational. It doesn't repeat decimal values. You can write them out just like pi. Write them out from now till the cows come home. You'll never repeat a pattern, okay? Consistently. It's 2.718, blah, 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 and there's no pattern from there on. Irrational number, okay? And this is called your exponential function. So the E kind of stands for exponential, but not really. This number was first described, defined, I don't know what you would say, by a very famous mathematician, Euler.
I want to do my paper on this.
Okay.
Because I've heard about it, and I don't know, it's always piqued my interest. I really want to dive into it, so I want to do my paper on this.
Okay. On Euler or on the number E?
The number E,
oh,
I'll
okay.
probably tie it in with
Yeah, you probably will. Yeah. Hard to not. Okay. Yeah. And this is a feature about the exponential function e to the x. Its derivative is e to the x. And later, when we do integrals, the integral of e to the x is e to the x. I mean, can't get any easier than that. Okay, except go to the constants being 0. I guess it's easier. Okay, we're almost there. Now, it says here, there's a little side note here. In some ways, the number e is complicated, they put in quotes. It is irrational. It cannot be defined without using limits. However, the elegant formula, d by dx of e to the x is e to the x, show that e is, in some senses, simple from the point of view of calculus. F of x equal e to the x is simpler than the seemingly more natural exponential functions, f of x equal 2 to the x or 10 to the x or something like that. E to the x is just a beautiful, beautiful function. Okay. Now, in doing the proof here,
hold on. Where are we at again?
on page 127.
I can't go by that because my book's numbered a little different.
Really?
Yeah. For some reason.
Your page 127
Yeah.
doesn't start with the derivative of fx equal e to the x?
No, 127 is 3.6.
Say again?
Page 137 is section 3.6. So
Wow.
I'm all the way back in 111.
Okay.
But I don't
Find theorem 5.
Where was that? Theorem 5? This is the, let's see, differentiability implies continuity. Is that word?
No.
Okay. Great. I'm so happy that I don't have.
Okay.
It was the slide you just showed. You just showed about the natural number e.
Yeah.
That's all. It's just perfect.
Wow. It seemed like to me this is a weird place to do it. And in your book,
I can look it up in the index and see if it's somewhere else.
yeah.
I didn't mean to stop you. I would get to your book. Yes. So I don't know if I got it wrong.
Okay. have the same covers and everything, but here's the difference.
Oh, good. Oh, good.
Yeah. Everything else is the same, but you don't have a book with you. This is early transcendentals, and E is a transcendental function.
Oh, good.
So, I don't know where you're going to find that in your book.
Let me see if I can.
Look
So
up
I'm
exponential
last
function.
semester, I guess I never.
Okay. What your theorem
My
5
theorem
is
five.
our theorem 6.
Okay. Okay.
But,
Hey, let's see what.
no. You're going to have to look up in the index exponential function. See if it's even there.
Exponential probability functions. Okay, so 321. Exponential functions.
Okay, yeah.
Is that it?
You're pretty close to it here. We're going to be doing this.
That's it.
And they're going to
Okay.
amazing.
Cool.
I didn't realize they had one without
I'm
early
sorry.
transcendentals.
I got this book last semester online. I guess I just never, because it's so, everything's the same other than just a few, so I guess I was just kind of chugging along and just didn't pay attention to it.
Okay. So you jump over there. What chapter is that?
That is, I would have closed it. It's
320
it
something.
was like chapter 7 for me.
Okay, what's the name of the chapter at the top of the page?
Exponential functions, and that is the derivative of.
Wait, did you say chapter 7?
Uh-huh.
Wow.
Chapter 7, page 323, and the section is called the derivative of, or the exponential functions.
Yeah.
Yep.
Bizarre.
I'm sorry. But
No. Okay. So for you, jump over there, and basically what we're doing here is the same as what they're doing there. Okay. It doesn't look like quite the same order, but see, you conclude with this. This one starts with that.
I'll take I'll write a note in here. That way next time I can just flip to it.
Okay. Now, they're dealing with this. Okay. I guess what we'll do is start with the proof there, which precedes that thing here. The proof comes first in your book. But that's where we'll begin next time. We've run out of time, unfortunately. But let's see about homework exercises.
I'll try to go a little bit ahead and try to look at it.
Okay. Homework exercises: do any of the odds 1 through 5, any of the odds 7 through 13, any of the odds either 15 or 17, or both if you choose. And I would stop there, and we'll pick up from there and go from there. All right, good deal. Interesting. Well, I've got